Okay, this is the second video for section 10.1, which is two proportion Z inferences. The first video dealt with, basically all the major stuff in regards to section 10.1 and making a two proportion Z interval or doing a two proportion Z test, and then before that the sampling distribution of the difference there. But this one deals with an experimental design situation, which we've kind of been talking about all year, since chapter 4. It's important that you're able to recognize when you have an experimental problem that's an experiment versus a problem where you have random sample. So there's two aspects of the word randomness that it's critical that you understand. Is when you take a random sample from a population, the big deal there is that you can now generalize about that population. Okay, that random sample, because you've gotten it randomly, it should be a representative sample that should even out influences of other variables, and so you can infer about that population. The other aspect is if you have random assignment to treatments in an experiment. If that is the case, you can infer a cause and effect relationship amongst people, animals, or things that are like these things you're working with. So that infers a cause and effect. So one of them allows you to infer, allows you to generalize about a larger population. The random assignment to treatments in an experiment allows you to establish a cause and effect relationship. So let's just go ahead and do this problem. It says a medical researcher wishes to see if a new post-surgical pain reliever works more effectively than a current reliever. Notice it says more effectively, not just differently. So we'll talk about that in a second. He randomly assigns 200 surgery patients into one of two groups. 100 will get the new drug after the surgery, while the other 100 will get the old drug after the surgery. Now, so we have randomly assigned them to groups. It doesn't say how we got these 200 people. We didn't, and so we don't know that they were gotten randomly. They probably weren't. Okay, because in general, you can't randomly select people to be part of medical experiments. They have to volunteer for it. And so the only people we can infer about, and what we're going to have to say later in the problem, is patients like these. Patients like these. We have to use, in essence, that term. So anyway, so this is a little bit different sort of problem. So we have two groups. 100 will get the new drug after the surgery, and the other 100 will get the older group. In the new group, 85 of the 100 reported no pain in the day after the surgery. In the old group, 74 out of 100 reported no pain. Now, this is the second example where I've used the exact same size to it, which I probably shouldn't do that because that may make you think that's a requirement, and it's not. It wouldn't be a big deal if this was like 100 and this is 150 or something. I mean, if they're like way different, it could be an issue. If it's like there was 50 here and there's 500 there. I mean, but anyway, in general, these don't have to be the same size. So the premise of what's going on is, okay, in the new group, so I'll call that, just so I can see this, so my p hat, my sample proportion for the new drug group, and then we got the old drug group, so I'll call this a piece of n for my new group, and so that is 85 out of 100, so that p hat is 0.85. And then for my old group, my p hat sub old, or you could call this 1 and 2 if you want. I like using letters so I don't get them mixed up later on. So this is 74 out of 100, and that's 0.74. So the premise of this is that, well, the new group in this sample, certainly more of them reported no pain in the day after surgery. So it appears to be better, okay, than this one. But is it so different that it's beyond sampling variability, beyond just random chance? In other words, it's plausible that if we did it with 100 more patients like of each of these, that, we would get 80% here and 74% here or something like that. Okay? So how plausible is it that these two things are different by sampling variability? Or is it so different that we are going to say, this is really strong evidence of a difference in the population values for all patients like these. So, all right, so here we go. Create a 95% confidence interval for the difference in the proportion of patients like these, see it use that phrase, that will experience no pain with a new drug and the proportion of patients like these that will experience no pain with the old drug in the first day after surgery. See, these are, in essence, sample values, okay? And they are estimates of the population value. And the population value is all patients like these. It's the proportion. So this one, our P sub n without a hat, the population proportion is the proportion of all patients like these who take the new drug that experience no pain. And then P sub G, this second population here, is all patients like these, not P sub G, it's P sub O, sorry. I'm still in my mind in that last problem. But anyway, it's all patients like these that take the old drug that experience no pain. So these are estimates of those population values. All right, our type of inference, so we're asked to make an interval, so we do the TAME acronym. So our type of inference is going to be, this is a 2 proportion Z interval. 2 proportion Z interval. There we go. And if you can say that, you get 1/4 of the problem right. All right, so then our assumptions. Now remember, in our 2 sample stuffs, I told you it was I-SIN. I-SIN. In other words, independent random sample, or SRS, and then independence, our population size at least 10 times our sample size, and then we've got normality. All right, and so what you can say here is this. What you can say is, it says they were randomly assigned, so independent, random condition is met for patients like these. There you go. It's a bit more cumbersome than what we've had in the past, but that was the way you should say it. Now, the thing about it is, our independent, now, good news about something that's either is, of course, this one is our population sizes have to be at least 10 times our sample sizes, and it wouldn't be, you could say, well, there has to be at least 1,000 of each people like these, but because we've had no sampling, we don't have to do this, because we haven't sampled here. We've just taken volunteers. We've taken these 200 surgery patients. So when you have an experimental situation, you don't have to worry about checking that. Okay, so that's kind of a bonus. Now for our normality, and it is the same. No, and with a proportion, n times p and n times 1 minus p had to be greater than or equal to 10. But we've got two groups here in essence. And so we have n for the new drug, n for the new drug, and then we've got it for the old, n sub old drug. So n times p old, and then n of old times 1 minus times p. All of these have to be bigger than 10. So this n sub p, that's in essence our number of successes, 85. I mean, n is 100, and that's 85 over 100, and these are hats. Sorry, these are hats. These are hats, because we don't know the population values. If we did, all this would be pointless, because that's the whole thing. We're trying to estimate the population values. So this would be 80, 85, and then 15 failures. That's our number of successes, number of failures for the first group, and this would be 74 successes and 26 failures. They are both greater than or equal to 10, so thus normality is met. Thus, normality is met. In other words, the sampling distribution of every possible value of p hat sub n minus p hat sub o is approximately normal, like we talked about in that last video. So, so there that is. So there's our inference. Now our mechanics. Now I'm not going to write out the formula like that. You can certainly look at that last interval. I'm just going to use this calculator, and this is, you just have to write the interval. Yes, you need to understand how to use the formula, how to find the standard error, how to obviously the critical value, be able to state the margin of error. There's your formula for your standard error that you would do, and to be able to calculate it by hand, but I'll just use the calculator here. So we go stat test, and we're looking for a 2 proportion Z interval. 2 proportion Z, there it is, option B, all the way down there. So the 12th option I do believe, yeah. And so option B, so we hit enter on that. And so we've got 85 out of 100. So, and then we've got 74 out of 100, right, like that. And so there we go. These are pretty small sample sizes for proportions, by the way. And we are asked to make a 95% confidence interval, so we go 0.95. And so there's our interval. And so our interval is that. So for our mechanics, in essence, all we have to write down is this thing, which would be negative, and that is, what that is, that's 8.5 times 10, so that's 8.5 times 10 to the negative fourth. That's not negative 8.5. It's negative 8.5 times 10 to the negative fourth. That's an important issue. It's really close to 0, actually. 0.22085. And so there's our confidence interval. So I tend to convert these into regular decimals, and so what this means, this number is negative 0.0003085, and then 0.22085. And so there is my confidence interval. And then so for our ending, that's our mechanics. That is our mechanics. And so our ending, our stating, our drawing our conclusion in context, you would say this: I am 95% confident. I am 95% confident that, and then we would write that interval, negative 0.00085 to 0.22085, okay, captures the true difference, captures the true difference in the proportions of patients like these. And that's the main reason I wanted to add on this video, because this is obviously really similar. Like these, patients like these. That's what you have to say when you have an experimental situation where you don't have random selection. You have random assignment, because you can only infer, you can't, because you haven't had random selection, you can only infer patients like these. True different patients like these that take the new and old drugs that have no pain the day after surgery. That's certainly a bit cumbersome, but that's what it is. And of course, really, whenever you do this two sample stuff, is the most interesting thing is whether or not zeros in that interval. Because what we're estimating is we're estimating the proportion in the new drug group that experienced no pain minus the proportion of the old drug group. Since zero is not in the interval, 0 is a plausible value for that. But I mean, it's really close to the edge. But as a matter of fact, a lot of times in a situation like this, because of round-off error, it would put 0 on the outside of the interval. But they try to not put that sort of thing in the AP exam, I would say. But sometimes because of round-off error and things, that can happen, especially when this is so close. I made up a problem where this is really close. So anyway, so now that we're asked to do the test. So perform a test of significance to see if there's a significant increase. Okay. Yeah, this is the other thing. This is going to be in essence a one-sided test. That relationship I just talked about with you here about 0, that works if it's a two-sided test. But this is going to be a one-sided test. So, okay, we'll talk about this to see if there's an increase in the patients who report no pain between the new and the old drugs. All right. So our type of inference. Is going to be this. This would be a 2 proportion. So this is a 2 proportion Z test. Okay. Now our hypotheses. Null hypothesis that there's no difference is that P sub n is equal to P sub O, Our alternative is what we suspect might be true, and it is asking us to test for an increase. In other words, the proportion of patients like these who take the new drug that have no pain is greater than those that have the old drug. Okay? Now, the other way of writing this, as we discussed in the last video, the null hypothesis would be P sub n minus P sub O is equal to 0. The alternative is that P sub n minus P sub O would be greater than 0. That would be, in essence, saying the new drug works better. And we have to define P sub n and P sub O. P sub n is equal to the proportion of all patients like these. That's the whole reason I'm making this video, is so that you will learn to say, whenever you have an experimental design situation, we have not had random selection, so we can only infer about patients like these. All patients like these that take the new drug that have no pain the day after surgery. And then P sub O, you just use ditto marks. The only thing you're going to do is you're going to change this to the old drug. The old drug. So the old drug. Okay? The null hypothesis is, in essence, that there is no difference. The alternative in this case is that it's going to be greater than. Now our mechanics. So our mechanics, we come up with our test statistic p-value. So our test stat is going to be z, and we'll use our calculator to find this. Once again, on the last video, I showed you how to use the formula to get this. So how to use the formula, but I'll just use the calculator here. And so I go stat, tests, and I scroll down to 2 proportion z-test. Boom. Now, and it went ahead and entered those values for me. That's good. Now, if we had done a two-sided test, by the way, notice the p-value is slightly above 0.05. And that was what I was saying up here, is 0 is in the interval, so we're expecting a high p-value. It's a plausible value. The null is plausible, okay? So it should generate a high. We shouldn't reject it. Because it's a plausible value, it shouldn't be rejected. It has a high p-value. And that's what happens on a two-sided test. But on a one-sided test, and that works when you have 95% confidence, it goes with an alpha of 0.05. If it's a two-sided test, if you have not equal to. But for a one-sided test, that alpha gets divided in half. It gets divided in half. So let's see what happens on our one-sided test. So if we do a one-sided test, we go stat, test, and we're going 2 proportion z-test. Now we're going greater than. We're going greater than, and we go calculate, and we get it's 1.9267. So that is equal to 1.9267. Notice the p-value is 0.027. So the p-value is equal to 0.027076 approximately. Okay? And so there you go. And so you would say our ending is like what we said before. This p-value, which is 0.027076, is less than 0.05. Thus, I reject. The p-value is low. You reject the null. Thus, I reject the null hypothesis. Thus, I have convincing evidence for the alternative. Convincing evidence that, and then you state the alternative in context. I have convincing evidence that the proportion of patients like these that take the new drug that experience no pain in the day after surgery is greater than the patients like that who take the old drug who have no pain in the day after surgery, which is cumbersome to say, but you'd have to write all that out there. And once again, I hate that you have to write all that out. I don't like it, but it is what it is. Now, So let's, in regards to connecting the p-value with the interval. Now, so like I said, in conclusion, in regards to this, 0 is in the interval. So in a two-sided test, our p-value will be above 0.05. But on a one-sided test like this one is, one-sided just greater than, it gets put in half. So 0 is in the interval. So we're expecting our p-value to be above 0.025. And it is. It's 0.027, okay? But if we had an alpha of 0.05, we would reject it. With an alpha of 0.025, we would fail to reject it. So that is, in essence, the connection that happens here. Hope that's not too confusing. But anyway, thank you for watching the video, and now it's on to section 2. Oh, and you get a... You get another smiley face. There you go. Thank you for watching the video.